Copy the same parking distance warning function from vehicle A into vehicle B. If your idea of software reuse is copy, paste, rename a few files, and fix whatever breaks, you have created a second software version. You have not really solved reuse. The useful question is this: what would have to remain stable so that the same functional software could be used again without dragging every hardware, supplier, and project-specific dependency with it? That is where standardization becomes valuable. In the previous lesson, we looked at the AUTOSAR ecosystem. Different companies can contribute requirements, software, microcontrollers, tools, and integration. For those pieces to be reusable across projects, they need common technical contracts. AUTOSAR's primary goal is to standardize selected basic system functions and functional interfaces so software can be integrated, exchanged, and transferred more systematically. Start with the word standardization. Standardization does not mean every car contains identical software. It does not mean every supplier must use identical source code. And it does not mean manufacturers give up the algorithms that make their products different. Think instead about what happens at a boundary. Suppose a parking distance function needs 4 distance values and a vehicle state information. If every project gives those inputs different meanings, different data types, different units, and completely different access mechanisms, the application becomes expensive to move. A stable interface contract changes that. The producer and consumer can agree on what information is exchanged, what it means, and how it's represented, while the internal algorithm on either side can still be different. AUTOSAR explicitly treats standardized application interfaces as a major enabler for reuse and exchange. It generally does not standardize the internal functional algorithm of an application. It standardizes the information exchanged, where common agreement is useful. Now, define reuse carefully. Software reuse means deliberately using an existing software asset again in another appropriate context instead of rebuilding the same responsibility from zero. But reuse has levels. At the application level, a software component may be reusable when its external dependencies are cleanly defined. At the platform level, basic software implementations and standardized module concepts can be used across multiple ECU projects, subject to vendor, release, hardware, and configuration constraints. At the interface level, common data definitions reduce the need to redesign communication contracts every time 2 functions are connected. And at the engineering level, templates, configuration patterns, and tool exchange descriptions can reduce repeated work. These are different kinds of reuse. They should not be collapsed into the claim that one binary can simply be copied into every ECU. Return to our parking distance example. In vehicle A, imagine the application receives 4 logical inputs: front left distance, front right distance, rear left distance, and rear right distance. It also receives a vehicle state input telling it whether parking assistance is active. The application calculates a warning level and produces a logical output, such as parking warning level. Now move the function to vehicle B. Vehicle B may use different ultrasonic sensor electronics, a different microcontroller, a different network mapping, and a different ECU allocation. If the application directly knows sensor registers, CAN frame identifiers, ADC channels, or vendor-specific driver calls, those differences leak into the functional software. But if the application depends on meaningful interfaces while the lower software handles the implementation details, much more of the functional logic has a chance to remain reusable. On the classic platform, this separation is supported by software components, the runtime environment, and basic software. From the application's point of view, the virtual functional bus concept helps decouple functional communication from the detailed infrastructure used after ECU allocation. This leads to an important phrase: reuse is enabled by stable boundaries. Consider two software components. One produces vehicle speed, another consumes vehicle speed. The consumer should care about the agreed meaning and representation of vehicle speed. It should not need to know whether the producer reads a wheel speed sensor locally, receives information through another ECU, or changes hardware in a later vehicle generation. That is the benefit of encapsulation. Standardized or well-defined interfaces reduce the number of assumptions that cross component boundaries. AUTOSAR's application interfaces go further in selected vehicle domains by standardizing syntax and semantics for exchanged application information. But don't make the opposite mistake. Not every interface in every AUTOSAR project is automatically one universal AUTOSAR standard signal. Projects still define and configure many project-specific relationships. The real lesson is that common interface definitions create a reusable contract where standardization is appropriate. The same idea applies below the application layer. Communication, diagnostics, operating services, memory services, ECU state handling, and hardware access appear repeatedly across automotive ECUs. If every project invents incompatible architecture and APIs for those responsibilities, application reuse alone is not enough. Integration still changes dramatically from ECU to ECU. So AUTOSAR standardizes a basic software architecture and many interfaces around these recurring infrastructure responsibilities. A vendor can implement those specifications. A project can configure the implementation for its ECU. The actual source code can still differ between vendors and releases. So when engineers say AUTOSAR supports reuse, part of that benefit comes from reusing software, but another part comes from reusing architectural knowledge. An engineer who understands the role of the runtime environment, communication services, diagnostics, memory services, and microcontroller abstraction layer does not have to relearn a completely different software philosophy for every conforming project. Now we reach one of the biggest practical benefits: controlling version proliferation. Without disciplined reuse, one project becomes version A. A hardware change creates version B. Another customer creates version C. Then a bug is discovered. If the versions have drifted apart, the team may need 3 fixes, 3 integrations, and 3 verification campaigns. AUTOSAR's own material identifies reduction of version proliferation and increased software reuse as expected benefits. But the solution is not to force every vehicle into one configuration. AUTOSAR also emphasizes modularity, configurability, and scalability. The reusable part can remain stable, while configuration and genuinely different product requirements vary. This is the balance beginners should remember. Reuse what is truly common, configure what should vary, and redesign what is genuinely different. Trying to reuse the wrong thing can be as dangerous as duplicating everything. There's also a quality argument for reuse, but it needs careful wording. A component used repeatedly across projects can accumulate test experience, defect fixes, integration knowledge, and operational maturity. AUTOSAR describes increased maturity and quality as a potential benefit of greater reuse. That does not mean reused software is automatically safe or correct. A component proven in one ECU may face different timing, memory, safety, cybersecurity, or hardware assumptions in another. Its configuration may change. Its surrounding interfaces may change. The target vehicle may have different hazards and requirements. So reuse does not eliminate verification. It changes the starting point. Instead of beginning with an entirely new implementation, engineers begin with an existing asset whose assumptions must be checked against the new context. That's controlled reuse. Now, compare three phrases that are often mixed together. Reusable means the software was designed so it can reasonably be used again. Reused means it actually has been used again in another context. Portable means it can be moved between environments with limited adaptation. These ideas overlap, but they are not identical. AUTOSAR improves the conditions for reuse and transfer by creating standardized architecture, interfaces, and abstraction. It does not promise perfect portability. A new ECU can still require new configuration, generated code, resource analysis, integration, calibration, safety work, cybersecurity work, and testing. And hardware independent does not mean hardware blind. Execution time, memory, peripherals, electrical design, and physical I/O still matter. If someone tells you AUTOSAR means write once, run on every car, that is the misconception to reject. For an interview, the strongest answer is not simply AUTOSAR enables reuse. Explain why. AUTOSAR supports software reuse by standardizing selected architecture, basic system functions, interfaces, data definitions, and engineering descriptions. Those stable boundaries reduce unnecessary coupling, so application software components and infrastructure can be transferred or reused more systematically across ECUs, vehicle variants, suppliers, and projects. At the same time, configuration, hardware constraints, algorithms, integration, and verification remain project-specific. That is the balance between standardization and differentiation. The parking distance algorithm can remain a competitive implementation. The interface around it can be stable. The underlying ECU infrastructure can follow common architectural rules, and the project can configure the complete system for its actual vehicle. Subscribe if you're building this automotive software knowledge step by step and want the architecture to feel connected rather than memorized. So far, we have discussed the reasons, problems, ecosystem, standardization, and reuse. In Lesson 17, we finally open the AUTOSAR Classic platform itself and see how application software, the runtime environment, and basic software turn these ideas into a concrete ECU architecture.